What's up, everybody? Today we're going to talk about stability analysis on a region. And when I say region, I don't want you to think about not necessarily about a ball, like a circle region or in two dimension when we're talking about it. However, this type of region we are going to be interested in this video. And this is the system. And the question that we're being asked is the following: consider the stability with the constraint that, okay, this is the constraint. Right. So anyway, you know, I don't know, it is DAE, I guess, right? Differential algebraic equations, and meaning they are differential equations, but they evolve on a, like the trajectories evolve on a some stat that has been also identified or summarized in terms of algebraic equalities, right? And yeah, for example, this has nothing to do with what we are going to cover, but you know, Bellman inequality. This system, this is inequality, and also this is a differential equation, right? And k is positive, and this is, we know that this b goes to 0, meaning this system is stable. All right, stable. All right, and okay, let's look at it. First, what we are going to do is the following: we will literally substitute 0, right, and cancel out this x1 dynamics, because we know x1, and sometimes people write it like that, which is the actual correct one. This means that x1 is identically 0, right? And okay, to prevent any confusion that people might have. All right, and this is the new dynamical system, right? This is 0, right? And this is also 0, and we have this equality as a result of this. Okay, so we will look at the x2 and x3 dynamics, and somebody gave us this Lyapunov function. Okay, and by using that Lyapunov function, we are going to prove x2 and stability of x2 and x3 dynamics. Okay, and let's take the time derivative. But before saying anything, I hope that when I say this is the Lyapunov function, some part of your brain says, wait a sec, this is not even like this. This is like that. Why? Because when this is the case, right? And this term is 0. And so wait a sec, let me try to explain what I mean. This is not the case for this system. V equals 0 when, only when x2 and x3 equals 0. This is not the case, right? When x2 equals -5 and x3 equals -5, for example, +5, this v is 0. So this is positive semi-definite, in fact, right? Okay. All right. So why this Lyapunov function is correct? And I would like you to have this. I would like you to be skeptical about this Lyapunov function before I prove that it is correct. And yeah, this is at the moment positive semi-definite, right? And what we need is a positive definite, right? Positive definite Lyapunov function. Yeah, right? These are the stability requirements. Okay. The only way this is 0 is this. But we also have this, right? Due to the differential algebraic and equality constraints, right? And rather, this is the set we are interested in. Okay, and let's look at this. let's say this is x3 and this is x2. Okay, this is the graph, and let's also try to look at this graph. Right, let's do this is x2, something like this, and the intersection point is this. Okay, all right. So this Lyapunov function so far is okay. What we are going to do is to derive the v dot term. Okay, this is v dot derivation. Let me zoom in on this. All right, this is the v dot derivation. Okay, and we also have u term, by the way. I hope you notice that. And the magical thing about this Lyapunov function is the following. When we, first of all, we don't have u term, right? Okay, yeah, we shouldn't have. And on top of that, v not having u, v dot also doesn't have any u term appearing in that. So this is the following. And again, like I stated here, this is not negative definite, but negative semi-definite. However, the same situation arises where the only time v dot is 0 is on this set. And since we also have this constraint, intersection of these two is this. Okay, and by using LaSalle's, okay, I will talk about that in a few, wait a sec, in a moment. All right, so far we have v and v dot. It is agreeable, right? All right, and this is something that I wanted to say. Using LaSalle's invariant set theorem. What was that? What was the theorem? And trajectories converge to, right? And by the way, this is what I'm talking about. And we have this, and maybe I should put it like this. And right, when we have that, we have ISF, stability in the sense of Lyapunov. Right, but this is not like A dot S, meaning asymptotic stability, right? We don't have, if we have that, that's right, we don't have asymptotic stability, meaning we don't know whether or not states go to converge to 0. All right, or origin, more possibly. Okay, and LaSalle's theorem states that when we have that, states will converge to this set. Okay, meaning intersection of, like, this comes from the dynamics and this comes from our Lyapunov function. Okay, and yeah, v dot being 0 term for this system is this, right? By looking at this, we can conclude that, and we can also have this set, and we also know that from the, wait a sec, from this, right, from this part, we can also conclude that states x2 and x3, x2 and x3 states will converge to the equilibrium point. Okay, hence the system is stable. Okay, conclusion: if x1 can be driven to 0 in finite time, yeah, all right, this is the interesting part now. Okay, so let me show that system. Okay, we have a system, right? And we have inputs, right? And somebody tells us, like, inside information. What is that inside information? If you have the ability to drive x1, right, identically 0 in finite time, and this part is important. I'm not talking about exponential stability or asymptotic stability even, right? I'm talking about finite stability. And when I say finite stability, I hope that some part of your brain or the part of your brain that stores sliding mode control kind of, you know, and gets excited. Okay, this was a weird way of putting it. However, we know that for the system, if x1 can be driven to 0 and infinite term, then x2 and x3 dynamics will be asymptotically stable, meaning they will go to 0, right? St goes to infinity. Okay, so whole system will be asymptotically stable is the point. Okay, and the question is how can we design a controller that would, you know, drive x1 0 infinity. Okay, and since we talk about SMC sliding mode controller, right, we will look at that. And here is the statement. Okay, and here is the controller design part. This is the system. All right, and first of all, there is no U term appearing in that. Okay, and so let's try to look at second, you know, and derivative of x1 state. All right, and the derivation is given here. Okay, and at the end of the day we have this. And what is interesting about this like line is that the factor that multiplies u is like this term, right, regardless of what x2 8 or x2 whatever here in this case take on, and will not be 0, meaning we can use some type of like feedback linearization. No, yeah, we use some feedback linearization ideas here in this problem. However, we can just directly use feedback cancellation or nonlinearity cancellation type of control algorithm. On top of that, we can also have, since we have the finite time stability requirement, we can also employ some type of SMC, right, sliding mode control type of strategy here. And this is why I kind of like that problem and wanted to have a, you know, a lecture video on it. Okay, so this is the term here, right? And this, let's say term, second term, is the term that we like to cancel it. Okay, so here is the term and here is the minus sign. Okay, and here's the important part. Okay, we will use this control algorithm. Why? Let me explain why. Okay, when we use this control algorithm here, and the more explicit form is here, and since if we have the ability, we wouldn't like to compute x1 dot, like dot of anything actually, right? Because it kind of complicates things. And since we have x1 dynamics, we can like compute it without taking any derivative. Okay, and what I am trying to say is this, and about the stability, closed loop dynamics are, at the end of the day, is this closed loop for x1 dynamics. Okay, and this is stable. And when I say that type of stable, I hope that you're saying why, right? And the proof is given here. And the basic fact is that there are, like, you know, first, second, third, and fourth quadrants, right? And we will look at these parts and these parts. And this is x1, right? This is x1 dot, I guess. And more on that. This is x1 dot. Okay. Minus 4 sine x1 and minus 0.3 sine x2. Okay, so let's look at the dynamics here. And this part, like first and third quadrants, x1 times x2 equals x1 times x2, like this term is positive here in this region, right? In the first quadrant. And also that also happens in this region, meaning the third quadrant. Okay, and when we have that, in a way, I will not go into much detail. Okay, and in this quadrant, and this dynamical system turns into this one, right? And let me also show that with another color, hopefully. Okay, I'm going to use purple. And all right, and in this like second and fourth quadrant, the dynamical system, this is the dynamical system we have turned into this one, right? And all right, and let me look at that. Okay, like this is the idea, basic idea, right? Okay, and we can use some type of Lyapunov type strategy. Wait a sec to prove the stability. Okay, now we are in the code section and I'm looking at my time. Okay, 15 minutes passed. All right, let's continue a little. Hopefully I will conclude in 5 minutes. All right, proving the stability for the system. And this part is YOLMIP, and I also use MOSEC for as an STP solver. Okay, and this is MATLAB, of course. And what more do we have? Okay, you only need MATLAB and MOSEC or STP33. Okay, this part is related to the part that we discussed in the beginning of the video, meaning the stability proof, and for a given dynamical system, stability on a set. Okay, and this part is related to that. All right, and here is the Lyapunov function that we use, right? Okay, like this code section tries to find the valid Lyapunov function to prove the stability on a given set, basically. Okay, and we know as procedure and like Lagrange multipliers type of, concept, and this is kind of related to that. And when I do this code section, I also use the insight information, and meaning I only look at the x2 and x3 dynamics because I know that x1 equals 0 and x1 dot equals 0, right? And so in the like to reduce the dimension of the problem, I use that I employ some type of like pen and paper type of computations. Okay, and however in this section I didn't do that. I just, and you can look at the code, and here this is the set and this is the set that we like to analyze the stability of the given system. And yeah, that's it. You can recover or find the coefficients of the Lyapunov function, right, which is a polynomial in terms of indeterminates, and indeterminates meaning here in this case x1 to x3, right, x1 x2 x3. All right, and these two sections are related to the stability on a given set, and this is the control and also the closed-loop stability and simulations. And let me look at this, and here we can see the contour algorithm, right? And I use of course some type of to reduce the number of lines or to increase the readability. All right, but here's the interesting part. This is not 100% correct. Like I should have written sine, right? But I wanted the system to have more like continuous type of dynamics in close loop, right? And if you are if you are employing that type of strategy, you should like I'm not going to talk more on this, but you have more things to do. But to me, just looking at the, simulation results is kind of okay. And of course, if you can, right, do the sine function. But if your numerical simulation to behave like, I don't know, what you would like it to behave, yeah, you might use that. You might check that function. Okay. But to prove the stability, you have more things to do, is what I'm trying to say. Is that, okay, you can find the code in GitHub, and thanks for watching, and don't forget to subscribe.